I wanted to finish up with Hooke's law. This time we're going to talk about when the motion is damped, but it's still free. Nothing is actually touching the weight except for perhaps the medium that it's in. So remember, we had m y double prime plus k times y was equal to 0. This is the undamped motion. Now what we're going to do here is we are going to add another term called beta of y prime plus k times y equals 0. This beta here will be unique to the material that the weight is operating inside of. So this term has some sort of damping that is proportional to the instantaneous velocity. And that's really the extent of how it's different, is it just adds one term to it. So in this situation, you may have, like, let's say we have, once again, we have our weight. But this time it's possible that the weight is submerged in some sort of a liquid. And so, maybe the liquid is here. So whatever this medium that it is in, so I don't call it some fluid of some sort, it could just be air, but whatever the case may be, is some sort of a fluid will slow the motion from going up and down, and that's where this beta comes in. Beta is associated, some sort of a constant that is associated with this fluid. So let's do an example. Example 1. A spring is stretched 4 feet by a mass weighing 8 pounds. The medium through which the mass moves has a damping force of beta equals radical 2. So we want to determine the equation of motion. So as before, we'll do the same things that we did. I need beta, which I'm given here. The mass I can get in a second. We have, and k I can get in a second as well. So from force equals k times s, same thing as before. We have the stretch is 4 feet, and the force was 8 pounds. So we'll take k is equal to 2. To get the mass, remember that 8 pounds equals mass times gravity, and gravity in the American system of measurement is equal to 32 feet per second squared. So my mass is equal to 1/4 of a slug. And now we're ready to set it up. Remember, the equation looks like this: my double prime plus beta y prime plus k times y equals 0. Let me go ahead and throw in my m, which I know is 1/4. Beta is radical 2. Of course, you should know it's probably easiest to multiply through by 4. Let's go ahead and do that. Y double prime plus 4 radical 2 y prime plus 8y equals 0. And let me go ahead and set up my auxiliary equation. Remember, I'm using r instead of m because m is being used for the mass. So our auxiliary equation is r squared plus 4 radical 2r plus 8. Set that equal to 0. I'll use the quadratic formula. R equals negative 4 radical 2 plus and minus square root. Now if I square 4 radical 2, that'll be 32. The a is 1, of course, the c is equal to 8. And you'll notice that the part underneath of the square root disappears. So this will just be negative 2 radical 2. Well, this has to have two solutions. So we have r equals the repeated solution, negative 2 radical 2, comma, negative 2 radical 2. So the equation of motion is quite a bit different this time. Now it's y equals c1 e to the negative 2 radical 2t plus c2 t e to the negative 2 radical 2t. This, of course, because of being the repeated 0. It might even be easier to factor out the e out, and I may do that if I think it will help. So let me rewrite this as e to the negative 2 radical 2t times c1 plus c2t. Suppose the mass is released from equilibrium with a downward velocity of 5 feet per second. So since it's downward, remember this counts as positive if it's downward, so it's plus 5 feet per second. It is released from equilibrium. So the fact that we're releasing it from equilibrium tells us that y of 0 equals 0. This will allow us to find one of the c's. So let's plug it into the equation. Y of 0 equals e to the 0 times c1 plus c2 times 0. Of course, this means that we just have c1 survives. And now my new equation of motion then will be y equals, now it's just going to be e to the negative 2 radical 2t times c2 times t. So maybe I'll rewrite this as c2t e to the negative 2 radical 2t. Now next the initial velocity is 5 feet per second. So I have this right here tells me that y prime of 0 equals positive 5. So let me go ahead and take the derivative here. Y prime equals c2 e to the negative 2 radical 2t plus, then I'm going to take the derivative of this stuff. Actually, it's not going to be a plus, it'll be a minus c2 t times 2 radical 2 e to the negative 2 radical 2t. And let me go ahead then and plug in 0. Y prime of 0 equals 5, so we'll plug that in here. I have 5 will equal, well, this whole piece just goes away, doesn't it? And we're left with just c2. So here's our equation of motion then. The c1 was not there, it was equal to 0. The c2 was 5, so it looks like 5 t e to the negative 2 radical 2t. One thing you should notice about this style of motion, if you graph it, it was released from equilibrium, but it had a downward force, but down is positive for us, so it physically goes the opposite of this, but look what we have here then. What does that mean? It will go, once it is released from equilibrium, releasing it downward, it'll go down as far as it's going to get, and then it will start to come up but slow down and ease off until there's almost no movement. It's asymptotic to x-axis. Determine the time and height of its most extreme displacement from equilibrium. So basically all that is to find this particular point up here, or you've done this in calculus a billion times. Take the derivative, set it equal to 0, and find out what that point is. So we'll set y prime equal to 0, and y prime is 5e to the negative 2 radical 2t minus 10 radical 2 t e to the negative 2 radical 2t equals 0. Now from everything in here, I'll be able to factor out the e to the negative 2 radical 2t. 5 minus 10 radical 2t will be left in the parentheses. E to the whatever is never equal to 0, so I'll wipe it out. And that leaves me with 5 minus 10 radical 2t equals 0. So 5 equals 10 radical 2t. I'll divide by 10 radical 2. And I'll get t equals 1 over 2 radical 2 seconds. So I've got one portion of this. The t value, remember this is actually the t-axis. I have 1 over 2 radical 2. Probably better to convert it to a decimal. Now let's plug it into the equation itself to get the height, the original equation. So y of 1 over 2 radical 2. That equals 5. And then you have the t part of it. So we have 1 over 2 radical 2. And then we have e to the negative 2 radical 2 times 1 over 2 radical 2. Of course, that'll just be e to the negative 1. And it looks like we have 5 over 2 radical 2 e to the negative 1. So there's the point that you have there. If you're looking for decimals, the decimal version of these, if you would like or prefer, is 0.354, comma 0.65. For my second and last example, because there's really not a lot to talk about here, it really doesn't change much of the problem from before. We just added a term. Here in this next one, we have a mass weighing 10 pounds stretches a spring 2 feet. Next we have a mass weighing 8 pounds is attached to the spring. And immersed in a medium where beta is equal to 1. So beta equal to 1 means that the retarding force of the medium is proportional to the instantaneous velocity. It actually is equal to the instantaneous velocity. If the mass is released from a position one-half foot below equilibrium with a downward force, I keep saying downward force, a downward velocity of 1 foot per second, determine the equation of motion. So first of all, let's go get the K. We'll start with K. I have 10 pounds, stretches the spring 2 feet. So we have K equals 5. Now the mass that we're throwing on the spring is 8 pounds. So for M, 8 pounds equals mass times gravity, or it looks like we have the same thing as before. M equals 1/4. Remember, these are measured in slugs when we're talking about the American system. And finally, beta is given in here is equal to 1. So let's go ahead and throw it into our equation. My double prime plus beta y prime plus k times y equals 0. Let's go ahead and throw in our mass. We got 1/4 y double prime plus 1 y prime plus 5y equals 0. I'll multiply everything through by 4, and I get y double prime plus 4y prime plus 20y equals 0. Let me get the auxiliary equation. I get r squared plus 4r plus 20 equals 0. So r equals -4 plus and minus 16 minus 4 times 20 all over 2. We have -4 plus and minus. This was obviously an example made to work out well. 16 minus 80 is -64, so I get plus and minus the square root of -64, or plus and minus 8i. So I get -2 plus and minus 4i. So immediately from that, we get that our equation of motion then is y equals e to the -2 t times c1 cosine 4t plus c2 sine of 4t. And there's my equation of motion. The next thing I'm looking to do is we had released from a point 1/2 foot below equilibrium. So what does that mean? That means that y of 0 equals 1/2. It's positive because it's below equilibrium. So if I throw in t equals 0 here, the sign will disappear, and it looks like I'll get 1/2 will equal e to the 0, c1 cosine of 0 plus c2 sine of 0. That'll just tell me that 1/2 equals c1. And so now my equation of motion is y equals e to the -2t times 1/2 cosine of 4t plus c2 sine of 4t. Next, we are told that the initial velocity was downward 1 foot per second. So the initial velocity is 1 foot per second downward. And that's the positive direction. So we have y prime of 0 equals 1. Well, let me go ahead and take the derivative of all this stuff. y prime equals, start with this stuff out here, negative 2e to the negative 2t, leave the inside alone, 1/2 cosine of 4t plus c2 sine of 4t plus e to the negative 2t. Now I'll take the derivative inside the parentheses, and I will get negative 2 sine of 2t. But then I'll get plus 4c2 cosine of 4t. 4c2 cosine 4t. And let's go ahead and plug in 0 for t. So I'll get 1 equals negative 2e to the 0 times 1/2 cosine of 0 plus c2 sine of 0 plus e to the 0 negative 2 sine of 0 plus 4c2 cosine of 0. A lot of stuff cancels here. 1 equals, for example, this sign goes away and so does that sign. E to the 0 is 1, so I have negative 2 times 1/2, that's this part right here. And then over here, I'll just get plus 4c2. So 1 equals negative 1 plus 4c2. 2 equals 4c2. c2 equals 1/2, just like c1. So my y will equal e to the negative 2t times 1/2 cosine of 4t plus 1/2 sine of 4t. Honestly, I think it might look just a teeny bit better if I pull that 1/2 out. I get 1/2 e to the negative 2t times cosine of 4t plus sine of 4t. Now this is a perfect example of what we talk about with damping. What's going to happen here is this e to the negative 2t. As t goes on, this is going to go to 0. It's actually going to go, it's going to get small very fast. This right here, this part is responsible for it going up and down, but this part dampens it out. It's a perfect display of what this whole section is about. So if you take just a real quick look at the graph, we started at 1/2 of a foot below equilibrium. Then what it does is it comes up to a high, and then it comes under like this. But you'll notice that this, it'll keep oscillating and theoretically oscillating forever. But the fact is that it's damper and it's getting close to slowing down. Eventually, the medium will completely stop it. Then all you need to do, I'm not going to go through the effort of taking derivatives and all that kind of stuff. You just use your graphing calculator, find this point, and you'll discover that it's 0.0804, comma, 0.539. So that means at time, not even 1/10 of a second, it goes, remember this was released at 1/2 of a foot or 0.5 of a foot below equilibrium. It's with a downward force. That means that it sinks just 0.039 feet lower, and then it starts to come back up. And as you can see, you can imagine the fluid slowing it down as it goes on and on.